Hello guys, and welcome to the Avionics Bench YouTube channel. Today we're gonna see how we can decode the ARINC 429 signals using a simple device, which is this guy here. It's a simple logic analyzer you can get from I think Amazon and AliExpress for I don't know 5 to 10 euros probably. So we are going to see how to connect such logic analyzer to unit. In this case I'm going to use this unit here. Is ACP used in Airbus A320 cockpits, and so we're gonna see how we can connect this to the logic analyzer, to this unit here, and then how we can decode the signals that are transmitted from this unit. How to decode so the ARINC 429 data, the label, the SDI, the word itself, the SSM, and the parity. So first of all, before going to the bench, let's see what is this ARINC 429. It consists of two differential lines, A and B, and the lines are differential. It means that when the A line is high, the B line is low, and vice versa. When the A line is low, the B line is high. The voltages involved are plus 5 volts and minus 5 volts. And in the ARINC 429, the plus 5 volt represents the 1 bit, and the minus 5 volt represent the 0 bit. This is a typical ARINC 429 data stream. It consists of 32 bits. If you count the bits 1 and 0, they are actually 32, and they are divided into the first chunk, which is 8 bits, which consists of the label, which is coded in octal, then the SDI, which is 2 bits, voila. Then the word itself, the data itself, which consists of 19 bits, then the SSM, 2 bits, and the parity, which is 1 bit. The parity must be odd. It means that this bit is selected in order to always have the number of bits associated to 1 to be an odd number. The speed of the transmission can be high speed, which is 100 kilobits per second, and low speed, which is 12.5 kilobits per second. In the last month, I developed actually a decoder which can decode from a stream of ARINC data the label, the SDI, the data, the SSM, and can also check the parity. So let's see now how we can connect the ACP to the logic analyzer. So we are back to the bench. I connected the logic analyzer to the USB port, so it's powered. You can see the red LED here, and I connected then the logic analyzer to the ACP here. It looks complicated, but is very simple. I'm actually using this logic analyzer has 8 channels. I'm using channel 1 and 2, and these 2 channels are connected here with a red wire and brown wire, and this goes to to the ARINC output of the ACP, and then there is also the ground here on this wire here. So about the pinouts on this circular connector, we are using 4 pins, which are this is the power supply, the ground, and the plus 28 volts, and this is the ARINC output, which then goes to channel 1 and channel 2. The pinout for this panel can be easily found on this website. And so once again we are using the power 28 volts, the ground, the power is on mic pin, the ground is on November, and then the ARINC output on hotel and golf. So I also connected 2 oscilloscope probes, but they are not needed in order to decode the ARINC signals. The oscilloscope's probes are connected to this oscilloscope here, so we can see what is happening on real time. And I also connected the ACP power lines to this power supply, regulated to 28 volts here. So the next step will be to go to the computer and start the logic analyzer program, which is an open source program called Sigrok, and in particular we are going to use the graphical interface called Pulse View. So just to show you another presentation of what we have just seen. So we have here the ACP, which is connected through the pin mic to 28 volts and November to the pin ground, and the ARINC 429 output from the hotel and golf pins are connected to channel 1 and channel 2 of the logic analyzer, and then the logic analyzer is connected to the computer. So here we are in Pulse View. This is the graphical interface for Sigrok, and I set up all the parameters to start the acquisition. I have the 2 channel DID0 and D1 enabled. For DID0 I enabled the triggering, the trigger for the rising edge. And I also set up, that's very important, the pre-trigger to 2%. This enables the acquisition to start a little bit before the trigger itself. And I also selected the number of samples to 1 mega samples, and the acquisition frequency to 500 kilohertz. That should be enough for decoding these ARINC signals coming from the ACP. The logic analyzer is also recognized already here. It's connected to my computer and it has been recognized. So in order to start the acquisition, we push this button here, run, and now we are in acquisition mode. So nothing happens because the ACP is currently off, but I'm now going to push power, so giving 28 volts, and we see something here. Something happened. We have a lot of data coming coming from the logic analyzer, and it's quite interesting to see what we have here. So as you can see here, that's apparently the first stream of data sent by the ACP, and we can clearly see, let me raise this a little bit to 70, yes, we can clearly see that the acquisition works because we have the differential signal. One important thing I didn't tell you before is that the logic analyzer I'm using uses only it can detect only positive signals. So here we are detecting only positive signals from the A and B differential line. So it means that when the D0 line is positive, the D1 line is negative, so we must have a pulse only on the D0 and not on D1. So we see, and the other way around. In this case, D1 is positive, so D0 must be 0. That's a good sign that the acquisition worked actually. And let's see if the rest worked. Yes, I see here a positive pulse, but none on D0. And yes, it seems quite correct. Now the next thing we have to do is to decode the signal. In order to do that, we push this button here, we click here, and there is this ARINC 429 decoder that I developed last month, which is quite useful. So you click twice, a new line appears here. We can close this window, and we can click on ARINC 2429, and the software asks us which signal is the B line, the A line, sorry, and which signal is the B line. If you don't know exactly what line it is, you can guess by try and error. You have just two possibilities. If you know what should be the labels, it's quite easy to guess. In my case, I already know that D1 is the A signal and D0 is the B signal. And here we go. We have three new lines appearing here: the bits, the word, and the parity check. If we look closely, we see that the decoder worked. We have the bits, so the decoder interprets these the D1 bits as the ones and the D0 bits as the 0. Maybe if I push up, sorry, if I put this in this way, maybe it's easier to see. Apparently what we have here is that the ACP, the first message sent by the ACP is labeled 300, coded in octal with SDI equal to 0 and data and SSM equal to 0. The parity is okay because we have the parity must be odd, so we have 3 bits equal to 1, this one here, then the second one here, and this one here. Let's see what happens next. We have this other label here 210 that has been also decoded correctly. The parity is fine, so it should be also successful. It's also interesting to see what is the space, the time space between two different words. And here we see that it's around 7.3 microseconds. And this is between the first and the second line. Between the second and the third line is around 17 microseconds. And then for the rest of the data, it seems to be always around 7 microseconds. So that's it for today, guys. I hope you liked. Please like and subscribe, and see you next time. Bye bye.